All right. I guess maybe it's not morning for you. It's morning for me. All right. Today we're going to look at logarithmic functions. And we've done inverse functions, then we did exponential, and logarithmic functions are actually the inverse of an exponential. So we're going to do a lot with just figuring out that relationship today between logarithms and exponentials. Now, because these are inverses of one another, we find ourselves switching between the two formats, between an exponential and between a logarithm. So just to see where do all the parts go when you're switching forms, because it's not quite as natural as squaring and square rooting, maybe, as inverse functions are. So here's what we did yesterday. Okay. That's my dog shaking like crazy over here. Okay, sorry. Here's what we had yesterday. It was an exponential. And so you have some base number here, and it's going to be raised to your variable. So it's raised to the x power, and then it would equal something. So if something is in exponential form, and you want to write it in logarithmic form, it's going to look like this over here. So the base of the exponential is also the base of your logarithm. And in general, logarithms are just exponents. And so it's the exponent that you want to raise this base to get to this number. So in my head, I always think, oh, the log equals the exponent, because you can see over here, here's the exponent. So the logarithm is equal to the exponent. This value that you're taking the logarithm of is called the argument. That may be a new term for you. Sometimes we don't really use that as much as we probably should. All right, so when we're working with logarithms, the base is raised to what power? So that's kind of what you're figuring. The base needs to be raised to what power to get this argument value right here. And so if I'm given this right here, I'm trying to figure out what power to raise that base to. All right, let's just practice doing some. So here I have a log, and this is the way this is worded. Everybody has a hard time saying this. It's read log base 5 of 25. Not log 5 times 25 or something. It's log base 5 of 25. Now, when you look at that, you're trying to figure out what exponent do I need to put on this 5 to turn it into a 25. Right? Well, that would be a 2. I need to take 5 to the second power to get 25. 7 raised to what power gets me a 7? To the first power. 4 to what power gets me a 64? All right, now right here, you're going to start to learn that it is helpful to know some of your powers when you are working with logarithms. So I'm going to do a quick side note. I'm going fast. You would want to know 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. At the bare minimum, you would want to know these. Maybe even a 2 to the sixth, which would then be a 64. Okay. But you also have to know more than just 2's. You got to know 3's. You got to know 3 squared is 9. You got to know 3 to the third is 27. You've got to know 3 to the fourth is 81. You got to know some 4's. How about 4 squared? How about 4 to the third power? Well, 4 to the third power is 64. Maybe even, how about 5 to the third power? I know you know 5 squared is 25, but what's 5 to the third? It's 125. You should know these and maybe spend a little time back in the good old days of doing flashcards when you were in the 4th grade learning your times tables. You got to know some of these numbers if you're going to be able to do logarithms. So right here, 4 raised to what power is a 64? 4 raised to the third power is 64. Now, I'm going to start getting a little bit fancy on it. Now, 4 raised to what power is a 2? That's weird because I'm getting smaller. What do I have to do to a 4 to turn it into a 2? Well, I have to square root it. And square rooting is what power? It is the 1/2 power. So if you ever want to square root, your power is 1/2. If you want a cube root, it's a 1/3. Fourth root, 1/4. Okay, look at this one. Now, the 2, I see there's a 4, so I feel like I got to square it, but how do I bump it to the denominator? Do you know how you move that to the denominator? You have a negative exponent is what moves it to the denominator. So 2 squared is 4, but because I moved it to the denominator, it's a -2. So 2 to the -2 power would get me a 1/4. Okay, you try this next one. 10 to what power is a 1/100th? Okay, that's also a -2 because I have to square it, but I have to bump it to the denominator. All right, now I'm going to throw some really weird ones at us. This one right here is not supposed to be tricky, but everybody looks at it like it's tricky. Like 4 raised to what power is 4 to the 8th? Well, don't go to your calculator and figure out what 4 to the 8th is. We don't want to do that. Think of it like this. 4 to what power is 4 to the 8th power? And all I got to do is figure out this number right here. So don't overthink it. It's just an 8. 4 to the 8th power is 4 to the 8th power. Okay, here's another weird one. When you see an exponential and a logarithm caught up together. All right, well, remember exponentials and logs undo each other. So the base of the exponential is a 3, but the base of this logarithm is also 3. So basically what's happening here is those powers and the exponential logarithm cancel each other out, and all you just end up with here is a 17. So don't overanalyze it. We don't spend a lot of time on this, but it does pop up randomly once in a while. The bases are both 3. I won't get tricky there. They'll always have to match. Okay, next one. 2 raised to what? Oh, we just did this one. I'm going to change it on us. Can I get you to change this in your notes to an 8? What if that was a 1/8? 2 to what power gets us a 1/8? Will it bump to the denominator? That's going to make it be negative. And 2 cubed is 8. All right. 16 raised to what power is a 4? Okay, I got to square root it. That's a 1/2. 8 to what power is a 2? I got to cube root it. That's a 1/3. 4 raised to what power is a 32? Okay, now that's really actually trickier because that does not work out nice. 4 squared is 16 and 4 cubed is 64. So it's somewhere between a squared and a cube, but it doesn't land perfectly. So what we do on problems like this is it's kind of twofold. First thing you're going to do is you're going to get this 4 and you're going to break it down so that it's smaller. So what I could do to this 4 is I could square root it. Now just watch here for a second. So what I would do is I would say, all right, well, I want to take my 4, take my 4, and I want to square root it. If I square root it, it's now a 2. And 2 raised to the 5th power is 32. So I'm doing two things. I'm going to take this 4, I'm square rooting it, I'm breaking it down, and I'm building it back up. So this power to a power, you just multiply. So 4 to the 5/2 power is actually equal to 32. The 2 square roots it, the 5 builds it back up to the 32. So futuristically, when I'm doing this, if I want to break it down, it goes in the denominator as a root, and then build it back up, it goes in the numerator. Now, I told you not to write any of that because this is not my answer. It is not 4 to the 5/2. Remember that the logarithm is just the exponent. The answer is just the 5/2. Okay, let's try another one. I'm actually going to skip this next one. No, I'm not. I'm just going to do it. Okay, so 16 raised to what power is a 64? All right, I've got to break it down first. So I'm going to square root the 16. That's now a 4. 4 raised to what power is a 64? To the 3rd. So my answer is 3/2. But I want to show you, I probably made that one a little bit too easy. In hindsight, I might change it, but I wanted to show you another way because 16, not only can you square root a 16, you can actually fourth root a 16. What's the fourth root of 16? It's 2. All right. So now I've got myself a 2. 2 raised to what power is a 64? All right, that's a lot. So 2 squared, 2 to the 3rd, to the 4th, to the 5th. 2 to the 5th I know is 32. We just did that one. 2 to the 5th is 32. I got to take it times 2 one more time. So 2 to the 6th power is 64. So I might have done that with it. But notice that 64 really just reduces back down to 3/2. So the first way I did it was fine, but if this number had not worked out quite so perfectly, I might have had to do a 4th root instead of a square root. So just be thinking about options that you have. Let's try the next one. It's a 27. What root can you do nicely to a 27? Yeah, you can cube root a 27. What is the cube root of 27? 3. 3 to what power is my 1/9? Well, I know 3 squared is 9, but I got to make it a negative to bring it down to the denominator. So negative 2/3 is my answer. Okay, last one. I have log base 1/2 of negative 1/4. Okay, now a lot of times people think that, oh, it's a 1/2, I'm going to have to do a negative exponent, but not really, because they're both fractions. Think of it like this. It's a 1/2 raised to some power to get a 1/4. So really, because it's already a fraction and I'm looking to get a fraction, I am not going to actually put a fractional exponent or a negative exponent. This would just be a 2, right? I could square 1/2 and get a 1/4. So ultimately, I'm thinking, oh, it's just 2, except that I have a negative right here. All right. So what can I do here to make this be a negative 1/4? Could I just make my 2 be negative? No. If the 2 is negative, what it does is it flips this. And so it would bring this 4 up. That's not going to turn it into a negative. There's actually nothing you can do to suddenly change the sign of it. So this was a trick question. There was a couple things I wanted to talk about because you will have some on your homework that do this, but that trick with sticking the negative right there, that's not possible. So we would just say that's undefined. You can't take the log of a negative. That's worth noting because that's going to come up futuristically. This particular problem is undefined. I'm talking about a lot of stuff, but none of that was really my answer. I can't take the log of a negative number. If you type it in your calculator, you get an error message on it. Okay, now in a perfect world, you have the worksheet that was kind of the in-class practice worksheet that we would have been working on. And I would highly recommend that right now, if you have that worksheet, you would pause and you would go do the front page of that worksheet. If you don't have it, it is homework, so you could print it off Google Classroom if you want to. And what it is just a whole bunch of these, getting really good at evaluating logarithms before we keep adding more and more to it. Now, once you have finished practicing that worksheet, then we're going to move on to the next thing. And again, you only did the front side because the back side is practicing what we're going to talk about right now. It's about switching from an exponential to a logarithm, which I mentioned earlier. Where do all the parts go? Well, here it is. 2 to the 3rd power is equal to 8. Yes, that is true. That's an exponential version. If I want to turn that into a logarithm, let's look at where all the parts go. Remember, this is the base of the exponential. It's also the base of your logarithm. Remember that the logarithm is really just an exponent. So you always set your logarithm equal to the exponent. And then the argument is what your exponential is equal to. Now, I kind of like to go from logarithm to exponential first because there's this nice loop action here. You take the base of the logarithm, you're going to raise it to this power to make it equal this. We always kind of think in our head this big loop. Now, the loop doesn't have to always go this way because sometimes we put the 3 over here on this side and it'd be 3 equals the log. So then your loop would go backwards, but that's the idea. The base raised to this power equals this number. So let's practice it a little bit. So this first one, you can see, oh, look, it's a logarithm. And somehow or the other, I would be eventually solving for x. Not what I'm doing right now, but I'm trying to solve for x. I don't like where the x is in the logarithm, so I'm going to switch it to an exponential. So let's look what that would look like. I would do the loop on it. 11 to the 2nd power equals x. 11 to the 2nd power equals x. Oh, so now if I was solving, I would know that x would be 121. But again, right now we're just switching forms, so don't go farther than what I've done right there. Let's try it again. This time the x is kind of caught up in the space. That's all right. Let's try the loop. X to the third power equals 512. X to the third power equals 512. And then if I was solving, I would cube root both sides. Again, not doing it right now. All right, let's practice going the other way. What if we have this exponential? This is kind of what we had yesterday. We had this exponent right here. Could we get that exponent out of there by switching over to a logarithm? So this is a log base 6 of 1,296 equals x. So now you have your log equals your x, equals your exponent. Let's try the next one. Log, what's the base? 15 of 1/225 equals the exponent. Okay, so there's just some muscle memory in remembering how that rearranges, and it's one of those things that you remember for like temporarily while you learn it in Algebra 2, and then you forget when you get to Algebra 3. So I want you to go ahead and do the back side of that worksheet, practicing, just get some muscle memory there on how to do the loop or how to go backwards from the loop and switch from logarithms to exponentials and vice versa. Okay, so at this point, I'm expecting you to be able to easily switch between the two forms, because now what we want to do is we want to solve. Now, there's nothing to be real fancy yet. These are pretty basic ones still. But let's practice switching forms to solve for our variable. So in this case, this first example, it's a logarithm. The x is the base. I'm trying to figure that out, so I'm going to do the loop. So x to the third power equals 8/27. Now to solve for x, it looks like I want to cube root both sides. Gave you some nice numbers there. They both cube root beautifully. The cube root of 8 is 2. The cube root of 27 is 3. Done. All right. What if my x is in a different location? What if the x is the argument now of the logarithm? All right. We're still going to do the loop. 4 to the 5/2 power is equal to x. All right, we did this earlier. Remember the little trick. The denominator is going to be the root. The 5, the numerator here is going to be the power. So 4 square rooted, that's 2, to the 5th power is 32. All right, one last one here. Now the x is over on the other side. It seems sort of like this would be one that you would like to leave like it is, except this whole logarithm stuff is a disaster. Look at that mess. Okay, so I'm going to go ahead and switch it to an exponential so you can see what I could do with this. I'm going to do 49 to the x power equals the cube root of 7. 49 to the x is equal to the cube root of 7. Now this feels like it's not ideal because the exponent just went up here, or the x, the variable, ended up tucked up here. But this is a problem from yesterday's lesson. Could you write both of these with the same, write both those as an exponential with the same base? Okay, hopefully your answer is yeah, I could write those both as a base of 7 because 49 is really just 7 squared to the x. And the cube root of 7 is really just a 7 to the 1/3 power. All right, cleaning that up, 7 to the 2x equals 7 to the 1/3. Once you get this, we call this a one-to-one way to solve exponentials because you got the 7 and the 7. So you can ignore the 7s and just look at these exponents here. The only way these two sides are equal is if those exponents are equal. So let's set those equal. Divide both sides by 2. Dividing by 2 is the same as multiplying by 1/2. So x is 1/6. All right, and then the last thing that we're going to talk about the kind of the basic stuff about logs, is knowing some of the main properties of logarithms. There's 3 properties we use all the time. And one of them is, and we call this kind of like expanding or condensing, because sometimes you want this all condensed into a single logarithm. It seems very simple when you can condense it to a single logarithm. But sometimes it's easier to work with if you expand it out into multiple logarithms. So anytime you're taking the log of something that is multiplied right here, you can actually separate it into the sum of two individual logs. Now, this only works if you have the base, the same base all the way through. So we call it base B. It might be base 3, base 7, base 10, who knows? All right, so multiplication separates into the addition of two individual logs. Well, so likewise, if you have division going on here instead of multiplication, you're going to do subtraction. And then the third one is that if you take m and you raise it to a power, well, really, that's just like an m times an m. If this was squared, let's say that was squared, then that's an m times an m. So really, I'm just doing this. An m times an m would be a log of m plus another log of m. And log of m plus log of m would be 2 times log of n. So what can happen is whatever that power is, you actually can just move it out in front as a multiplier of that. So anytime you see an exponent, pull it out in front of the logarithm as a coefficient. All right, let's try using it. I've got a bunch of examples here for us. Let's start with and the directions kind of vary on your homework, so make sure you kind of pay close attention to what they're asking you to do. This says, write the expression as a single logarithm. Okay, which seems basically, to me, you're just trying to condense it together. So let's give it a shot. We have log base 4 and a log base 4. That's good. Again, I'm not going to be tricky. They're always going to have the same base for you. Okay, so subtraction, remember, turns into division. So if I want to condense this, I'm going to call it log base 4 of 32 divided by 2. But then, of course, I'm going to try to simplify that. Log base 4 of 16. Now, looking at that, you should actually be able to easily then evaluate that log. That would just equal 2. But remember, the directions were just to write it as a single log. So don't go farther than that in this example. But you can see why it maybe would have been helpful to do that property, because it comes out real quick and easy here. All right, let's try again. On these two, do you see these coefficients out in front? Those are going to pop up as a power. So those are going to each go up there. So I'm going to have an x to the 6th. I'm going to have a y to the 5th. But I also have addition going on. And addition tells me to multiply those arguments together. So that's log base 2 of x to the 6th times y to the 5th. Okay, that's all there is to it. Let's try another one. Okay, this time still trying to condense. All I've really got going on is this addition of two logarithms. So let's just write log base 4. And then what I have to do, addition, remember, when you're condensing, you want to come back and multiply. So the 3 times the 5 will get me the 15. X times x is x squared. And we're done. Okay, let's try this next one. A little bit, well, I say a lot, little, I don't know, more going on, let's say. Here's what I've got. I've got a quantity here. That feels weird. Plus, I've got 3 different logarithms that I'm trying to condense into a single log if I can. And I can't. Every time I see subtraction, I'm going to do division. If I see addition, I'm going to do multiplication. So log base 3 of, I'm going to have this x plus 2, keep it in parentheses. This plus here is not the same as adding 2 separate logs. It's not that. This is just a quantity. The argument happens to be a binomial. Then I see subtraction that I'm going to turn into division and put an x down here. And then the next one's kind of the tricky one. It's addition. Now, so that I know that means multiply. You might be tempted to say, oh, I'm going to multiply this x here. but not really. It's not like that because it's really more like, let me undo that. It's really more like this. And that 2 would be like a 2 over 1. That 2 is actually back up on top. Now, you're going to see this on your homework a couple ways. Sometimes you're going to see this as a plus. Sometimes you're going to see it as a minus. In general, you just do each term. If it's a subtraction, it goes on the bottom. If it's an addition, it goes on top. So that 2 goes on top. Makes more sense to put it on the front there. I'm going to squeeze that in than to put it on the back end of that. Now, if you choose to go ahead and distribute that 2, that's totally fine. I'm pretty sure my math lab would accept that either way. All right, last one. This 1/2 comes up as a power. This 3 comes up as a power. So I'm going to have a log base A of, it's m to the 1/2, but I'm not going to write that. What is m to the 1/2 power really doing? It's really a square root. So don't leave it as a 1/2 power. Write it as a square root. And then I see a minus sign, so that tells me division of n to the 3rd power. Kind of a good habit to put parentheses around that. I didn't do it right here because there's just a single monomial, and it's not terrible as long as it's a monomial, but I sure like to group it together and say all of this is what the argument of my logarithm is. For sure would want to do it on something this messy. All right, got sidetracked there, sorry. Okay, let's try one more slide. Let's try going the other way. These are already all condensed together. What I want to do is I want to separate them out into multiple logarithms. We call that expanding. So when you look at this first problem right here, first thing I notice is there's no base. We actually call that common log. It's assumed to be a base 10. You may remember that. But just like if I would write a log base 9, or log base A, I'm just going to write this as a log and just have everything just be a log. Next thing I want to notice is what operations are going on. Well, I have multiplication right here, and I have division right here. So I see this as this is going to end up 3 separate logarithms. I'm going to start off, and I'm going to write log of 4. And then since it's being multiplied by the x, I'm going to put a plus log of x. And now I'm dividing, so now I subtract log y. Remember what I said earlier, anything in the numerator is going to be plus, anything in the denominator is going to be a minus. I'm done. That's all there is. Okay, let's take a look at this next one. It's a log base 9. This time what I see is a power. Do you remember that when you have, well, I'll just write it. It's going to be a log base 9 of x to the 4th minus log base 9 of 729. But I'm not done because I don't want to leave, you want your argument to be as simplified as possible on these. So this 4, I want to pull out in front. Now, next time you do this, you might be able to just do that in your head and do that all in one shot. Totally fine. You take as many steps as you need to expand and condense. As we get better, it'll take fewer and fewer steps. Now, the goal ultimately, now right now we are just expanding and condensing, but by separating this into multiple logs, oftentimes what can happen is you can start simplifying pieces of it, like this right here. Log base 9 of 729, you may not know this, but that's really just 9 to the 3rd power is equal to 729. So I could later on just call that a 3. That's going to be my goal later on. Okay, last one. This is a little bit messy. You got a cube root and a squared going on. That's kind of strange. Here's what I'm going to do with this one. I'm going to go ahead and rewrite this m squared to the 1/3 power, like that. That's what's really going on, which really means that it's a log base A of m to the 2/3 power when you multiply those exponents. And now I see, oh, okay, all right, that's an exponent. I'm going to pull that out in front. So final answer, log base A, I'm sorry, 2/3 log base A of m. Final answer. Okay, that's all we've got. There's lots of basic properties of logs that we're working through today so that we can build on that and do more challenging problems later on. Okay, hope this helps. See you later.